definition 11.3, limit convergence for sequences. And so I wrote a sequence is, and then we have, this is how Kawasaki represents his sequence with just that symbol. In the Belding-Mitchell book, they add this. Okay. And then what are these two terms? Well, it looks like they're the same terms. Convergence means that the sequence gone bad. Convergence means that the sequence has a limit. And what does a sequence? A sequence that has a limit means that that sequence converges. Okay, so let's delete that. And let's get going here. And so the definition of limit and convergence goes in this textbook. It has, so a sequence has the limit L, and in our book, in Belding and Mitchell, it's usually A when we deal with sequences, because A is the limit and a term is AN, right? So this L is usually used for functions. So this is, they're doing that because they didn't want to, it's an undergraduate textbook, they didn't want to introduce another. But this is better. So this is our limit and this is our term. Okay, and in the Bartle and Sherbert, they just use random. They'll say X. Has the limit L, or this is the same as the sequence converges to L. So if somebody says a sequence has a limit, what he's saying is that sequence converges to this number L, which is in the sequence. Okay, and then this whole business is denoted by limit as n goes to infinity of the sequence AN. And what you see here is in the limit notation, this is the nth term that we put here. Or, in fact, the formula. Yeah, so there is actual formula for this, right? It might be like this. Something like that usually goes here. The formula that generates each term of the sequence goes here. So this AN either represents the nth term, and the nth term is the formula term. Let's just write that here. Nth term is the formula term. The formula that generates each term of the sequence. Can you write this? B L. So this thing means that what this is saying is this: AN converges to L. how to expand this thing, right? So the expansion goes if for every epsilon greater than 0, there exists a positive number n such that so we're expanding this such that all terms an of the sequence are only epsilon away from the limit. The absolute value is an minus the limit times epsilon. Not times. All the terms an of the sequence are less than epsilon distance from the limit of the sequence. Yeah. Shit. Yeah. Good catch and good save. I'm like, why is he saying multiply? Because that's what I heard. So this is because of the absolute value, this represents the distance between terms an, each and every term an from L, and this distance is always less than this positive number epsilon. We can put this thing, so we got A1, A2, let's say A3 here, and then if there exists a positive number n, oh yeah, I forgot one last thing. Whenever, this is the key thing, let me write this with a, this was, good thing I was gonna draw it out. So if for every epsilon greater than 0, as in positive epsilon, there exists a positive number n such that an, small n, minus L is always less than epsilon. But that is all the terms of whenever n is greater than n. So what happens is, this is the key thing. This is the difference between the definition of limit. This is not what you will find in when you're doing functions. So what happens here is we got A1, A2, A3. These are all ANs, right? Yep. And so let's just call them ANs for just for the hell of it, just for now. AN, and then when our sequence hits this number here, it's going merrily, an 1, 2, 3, hits this n number. After n, all the,
things are going to cluster around L.
yes, sir. You've seen this.
We played with this, I didn't have this idea.
So you did not do this with,
We did proofs.
we went straight into proofs.
Yeah, when I showed up,
We were doing proof. Ah, shit. Okay. All right. So all these ANs.
Oh, I remember it.
Yeah. So these ANs are the ones that come after this AN.
Yep.
Uppercase.
Right, and going this will have this very big, yeah.
Here. Yeah. Okay. All right. And this is pretty good. I think that's all. If a number doesn't have a limit, if a sequence doesn't have a limit, it diverges. So no limit, sequence diverges. Good save again. And the epsilon is going to go right here and right here. And I think you'll remember this. If we switch these guys out, let's put 1, 2, 3, and then maybe the number 4 was here. Then we went back to AN. So this real number is going to be bigger than this real number. This was a smaller real number arranged by the positive integers. And then this is, and then when this, after this, all of them cluster around here, mostly.
There could be one over that
Or even more, maybe few. Of course, there's the limit too. The upper bound. Upper bound is sitting over there. We'll run into that later. There you go. Thank you for the save here. And this, yeah. I think I put too many lines. Let's see. And this one is the L.